Good afternoon, everyone. I'm Hua Li from with Alibaba Cloud, working in infrastructure service group, working for networking. And today, I'm very happy to have the chance to introduce have a brief introduced in Alibaba Next Generation Gateway and in its deployment and the solution we propose with DPU. And okay, yeah. For Cloud Gateway, we have actually two major role of the gateway. The first one is the Cloud Central Gateway, and the second is the Cloud Edge Gateway. We defined a generic model for the Central Gateway and Edge Gateway. So for the hardware and software, they are all the same. So I simply picked the Edge Cloud deployment scenario as an example to illustrate how we build the next generation gateway. First, as we can see, the architecture of the Edge gateway is layered from the line between above the orange line. We can see the cloud component. First one, we can see central cloud controller, which is used to used for control plane of our Edge gateway, and also used as the monitor center and management center of the cloud managed Edge gateway deployed far from the cloud. Another one is our public cloud. The public cloud actually stands for the public cloud services, common services for face to the customers. And we may see another part of the deployment. Our gateway is actually Edge gateway is actually deployed in the internet service providers data center. They are connected back to the central cloud via the internet. The Edge cloud actually works for two roles. The first one is they act as toll switches. In our deployment, we are using a active-active connectivity provided to the servers with two uplinks connected to a group of Tor server. Here we can see the SNA-1 and SNA-2. SNA actually is our we named that the Smart Switch. We will explain it later. And then for the application level, the Edge gateway also acts as a gateway service. It provides the capability of virtual tunnel endpoint, that is in-cap and decap the VXLAN header, and it also has the feature for NAT, that is network address translation and load balancer. So in this picture we can see that that is simplified the use case of our Edge gateway. So sorry. Then previously, what is the challenges with our current generation of the gateway? First one is difficulty for in situ dilation. That is, when we deploy our gateway at the customer side, it puts in the ISP's data center, and then when the service requirement, especially the bandwidth, is increased, we cannot easily expand or extend the bandwidth capability of our gateway. This is the first one, is for deployment. This is a deployment issue. Another one is when the current generation, we are using a switch plus a server implementation of the gateway. So when the device crashed, the whole device goes down, and we have only device level HA for our edge gateway. So when a new technology emerged, that is, the DPU can do the gateway feature. So we are thinking that if we can replace the switch plus server to a switch plus DPU card implementation, so that the HA may have a better HA solution. That is, from device level HA to per card level HA. The third one is our current implementation of the gateway is a switch plus a strong x86 server, and running the net service and the load balance service and the VTAP fully on the x86 server. Even though the x86 server is very strong with 56 core, it only processes 100 gig service, 100 gig traffic per second. So we are thinking about that if we can enlarge or increase the performance, especially the bandwidth, because usually in edge deployment, the bandwidth is the issue, not the scale. So when the DPU emerged, we are thinking that can we leverage the advantage of DPU to accelerate the stateful traffic, the session-related traffic. And the last one is that when we are trying to build our new hardware, there is several new technology, new DPU coming up. So when we want to build it, we want to test the performance of the new card. We have to build 3 different. For example, we are testing 3 cards. We are building 3 test bed to test that, and we have to do 3 times the job to bring up the device. So we are thinking about that if we have a way to decouple the service itself, for example, the NAT and LB we are doing, to decouple them with the technology itself. For example, different DPU running same NAT and load balancer logic running in different DPU with the upper layer code unchanged. So we think the service and hardware accelerator decouple is one of our goals. Simply take a look at the key performance objectives. Here we can see 4 dimensions per connections, routes we need. Actually, we need underlay and overlay LBN lookups, and the scale should be 1 million plus. And billing is an important part. We need 1 million plus meters and counters for auditing, meters for billing, and the security. So actually, we are modeling this gateway for all purpose. So one encryption gateway may be one of the use case. Okay, so here we have a more clear comparison between the current generation of the gateway and the next. Currently, we are current generation is that we have a 2RU switches. The switch also provide the toll connectivity, and we do all the our service, the load balance, net, and things on the CPU. In this implementation, we have full flexibility because all the service is software. It's running on the x86 CPU, and for the reason or challenges we mentioned previously, and most importantly, the DPU hardware emerges. So we are trying to move our network service onto the DPU and may replace the programmable switches with common switches. Depends on the requirement of programmability on the switch. And then DPU has actually seen by our developers is actually an ASIC and with the assisted common CPU on that. So we still have the flexibility and we have the performance. The flexibility actually because we can do it on the DPU's ARM CPU or RISC-V CPU, and we can also program our P4 programmable handling model in the DPU ASIC. So this is what we are trying to build. Okay, take a simple look at the hardware. We have a common ASIC, AT ASIC of the switch, and we have 2 cards, DPU, inside the box, and we have module, CPU module and BMC module for management and power management and monitoring things. And DPU have 2 NIC, and we connected to the front panel with 2 FXP ports by 400 gig. So, okay, then another part that is the important part is what kind of software architecture we are using. As the Smart Switch is a new hardware model, we are adapting the Sonic multi-chassis architecture for managing the device. Yeah, we can see we are running Sonic on the switch and running Sonic on each DPU. And here we can clearly see that the slow path on ARM and the fast path on the ASIC is actually separated. The fast path actually we can run on that is defined with a behavioral, with a model, with a processing pipeline loaded into the DPU ASIC, and then the first first packet processing or the creation of the flow may run on the ARM CPU. And we have a cloud managed controller that we in previous picture. The switch is deployed far away or in the cloud or far away from the cloud, but they have to be managed and the policy is populated from the service controller, that is the SDN controller, controlling the net service or the load balancing service. And the cloud management controller is for control and management and collection of operation data and monitoring system health, monitoring system counters and things like that. And this uses the GNMI interface. Okay, so this is a simple picture for how Dash work. First, we define the network services like net and load balancer or encryption gateway. The first thing we do is the modeling. Through the modeling, we define the pipeline, how to process a net flow or load balancer flow, and we finally the product of modeling is a net or load balancer behavioral model. This behavioral model can be described with behavioral model P4. And when different DPU vendors or different technology appears, the vendors of the DPU can adapt to can do the translation between the BM's P4 and the hardware P4 so that we can compose a full system to test. And when we are doing the modeling, we also create sonic integration test cases and conformance and performance test cases in this in the process. So when the vendor of DPU adapted their P4 to the behavioral models P4, they can test the performance. And so as the users, we simply put no effort or very, very small effort so that we can see if a new DPU can fit in our service. Okay, here is how we do the net service. That's an example. First, we define the net service in the net service behavioral model, behavior, and then we generate, we describe it with the net behavioral model P4 code. And then in this time, we also add sonic configuration and sonic configuration database schema. And then we add something to actually there are cases because the SIT is already a framework. We add the cases to test the net behavior and the configuration, and we can test the data flow. And also we are adding performance and conformance test cases in the framework, which is currently already provided by the dash. Then all of this is the user's view. The users actually means the network service provider's view. It's actually user-facing procedure to do this. And the only thing DPU vendors wants to do is adapt the net behavioral model and do the SIT and performance and conformance testing, so that the development is done. So it actually reduces all the time consumed by the user. Yeah, here is a simple processing processing behavior of the net service. This is for in the blue block. It's defined as the mandatory one is ASIC supported P4 programmed processing, and the slow path is optional for ASIC. If a new technology can support it in the hardware, we can the red part is placed in the hardware. Otherwise, it can be placed in the DPUs, ARM CPU, or the RISC-V CPU. So it's flexible. because the fast path and slow path is both of them can be defined, but depends on the hardware. We can support it in both in hardware or part of it in hardware, part of it in software to keep the flexibility. Yeah, and the next part is Sanjay to introduce how DPU can be fixed in our use cases.
Thanks, Clark. I'm Sanjay. I'm from AMD Pensando. Good afternoon. We've been working with Clark and team to enable this solution, to help them put this, get this solution running on the DPU. Very quickly, I'll just the way I'll present is I'll have a few introduce the hardware, then we'll introduce the software architecture that enables using this hardware, and then we get to what is the sonic architecture, and we'll leave you with those this thing. So this is the hardware. We have this is the DPU hardware from AMD. This involves mainly, I think, the main key components are there are 4 pipelines, and there is a 4+1 pipelines, which has a total of 144 MPUs for processing. It's spread as ingress, egress. There are a couple more RxDMA, TxDMA pipelines. Essentially, all of them are the same. But there are there's one that is more suitable to be used for ingress, one more suitable used for egress, etc. Apart from that, it's got 16 ARM cores, which could run the soft path that Clark was mentioning, the soft data path. Some of it that it could run there, and also has a bunch of offloads, which could do, for example, it could do IPsec and other offloads, compression and other offloads that are there are more engines sitting there, hardware engines. And incidentally, the pipeline is also capable of IPsec. So you could either offload some of the protocols to the IPsec engine, or there is also capable of a full line rate IPsec at 400 Gbps. Right? That's the hardware. It's pretty capable, pretty flexible, because there's nothing baked into it or hardwired into any of the hardware. So table sizes, for the most part, are pretty flexible. Right? So this is the software that allows exercising this hardware and being able to use this hardware. It's been shipping for some time. And what it ships with is there is a, of course, there is the kernel library, there is the Linux kernel drivers and DPDK driver, etc., to interact with the hardware itself. And on top of that, there is a platform library, for example, for handling platform-specific stuff like sensors, like interfaces and stuff like that. There is a platform library that is packaged. There is also some ARM sample code, and there is also P4 sample code. So these sample codes are typically more point solutions, for example, just for IPsec or just for NAT or just for policy lookup and stuff like that. Point this thing. Typically, I think to build a full-fledged solution like that was being presented here, one could use those samples or build on top of them multiple of them to build a full solution. Other than that, there is also the development toolchain also includes a complete build environment. It comes with a P4 compiler and a complete, to make it easier for the user, it comes with a full build environment. And also there is to speed up development, to iterate faster, there is a complete simulator, which is true to this thing. There is the simulator actually simulates the complete DPU model, the hardware model. So you could run it in a Docker container and simulate the whole pipeline, the apps, everything in the Docker itself. I know, to make it faster, then you don't need to go put it on the hardware, get it to boot there and stuff like that. So this is I think that was the hardware and the software. Now to get this solution going, this is the sonic architecture that, how the sonic was laid out. We ported sonic to boot on the DPU and on the ARM CPU and the hardware. And ELBA is the name for our DPU itself, the hardware. Apart from that, I think there are 2 buckets here in this picture to note. One is the one that's colored orange and yellow in those shades, and then one which is the green parts. The orange parts are essentially things that to speed up development, all the handling of the hardware, anything for pipeline initialization after building the complete pipeline, the pipeline initialization, any interface management in terms of getting notifications for up, down, or handling interfaces, anything that's got to do with the hardware, any platform management, all that is handled by the orange parts. So this we call as the core. Other than that, I think what we realized is the very common thing is the underlay. So this also packages the underlay, all routes management, routes, next stops, ECMP, all that is also managed, can be managed by the underlay. So all this is packaged as source code. So it's one could take it and modify it too, but you don't need to, right? You can, with the green parts, the solution, whoever is writing the solution could whatever the solution that's being built here, one could focus on, the developer could focus only on the business part of it, the actual, whatever we call as the overlay content, the actual data part, the application that we're trying to build, and focus and write it on top of this. So just a quick, this thing on there are a bunch of features. I think we just, I'm listing out some of these features here that is available on the SSDK, and a lot more coming. Right, and most of this come with samples, like I was mentioning, the P4 and also the source. So there is, for example, security evaluation or routing. All these are hardware features. There's also a hardware-assisted flow aging because very quickly with high speed, this thing will fill up the flow tables. So there's hardware-assisted flow aging. There's NAT. There's ECMP, complete full ECMP, VXLAN tunneling, et cetera, et cetera. So we've been, AMD and Pensando, we've been involved with Sonic for some time now. We have been contributing to Dash. We're trying to port this platform support onto Sonic. Right. So with that, I'll hand it back to Clark. He can.
Yep. Okay. This slide shows the current generation and the next generation. Some data from on the comparison. First one, we actually get instance 4 times the processing bandwidth for the for our application. Compared to the previous generation, overall TCL reduced by 50% because it replaced with the DPU. We saved a lot of on the strong x86 server, and stateful forwarding bandwidth just increased by 4 times because they are handled line rate by 400 gig processing speed. Yeah, and another advantage is that we can, for the edge use case, we can use a common switch rather than the programmable switch. And in the central cloud, we may also still select the programmable switch. This may also cut the cost of the device. Yep, that's it. That's all of them.
All right, thank you so much. All right, if you have any questions, you can reach out to Lei and Sanjay offline. We're running 15 minutes behind. We're going to do the next session immediately. Thank you.